Okay, a collection of A-level questions taken from WJC over the last 5 years or so. That's the old and the new specs, just for fun. So bromine reacts with methanoic acid. That's bromine, methanoic acid. Wanted to follow the rate of reaction. Mixed solutions, no concentration of bromine and methanoic acid. So there's two methods which the student could use to follow the rate of the reaction as it proceeds. Well, by and large, in the A-level, you've got a limited number of ways in which you can possibly follow reactions. First one of those is you can look at the color. You can use a colorimeter or a spectrophotometer in which the absorption at a particular wavelength changes with the concentration of the colored species. You can always mess around with gas production or loss because it changes volume. If gas is produced and you allow it to escape, it changes the mass and so forth. And then, of course, anytime you've got H plus or OH minus in there involved in the reaction, you can follow the reaction by checking the pH. So in this particular case here, bromine is colored. So you're going to start off with a colored solution. As the reaction takes place, that color is going to diminish as the bromine is used up. We're producing CO2, so the easiest thing to do would just be to let the CO2 escape and measure the mass of the entire reaction system periodically. You can collect it too and measure the volume as well if you wanted to, but in this case I'd probably just let the CO2 escape. And then of course we got H plus being produced, so the pH of the reaction mixture is going to go down as time goes along. Anyway, at the A level is going to be one of those three pretty much: color, mass change associated with gas production or loss, volume change associated with gas production, and so forth. Okay, magnetite mineral consists largely of magnesium carbonate. A sample of crushed magnetite, a mass of 6.72 grams. Excess dilute HCl, concentration 2 moles, placed in a conical balance. Carbon dioxide was given off because, of course, you have H plus, an acid with a carbonate. Carbonate is a base. The H plus is going to neutralize that base and makes CO2 as it does so. And here's the graph of the loss in mass. And that loss in mass is, of course, the CO2 just vanishing off. So we make CO2 rather quickly, then it diminishes off as we're doing it until ultimately it gets level there. Now, this first question is a terribly written experiment question. What one has to do is we're going to assume that find the graph for the time taken for half of the original mass to react. Well, the original mass is 6.72 grams. So half of that to react is half of 6.72. Obviously, that's not what they mean. What they presumably mean is half of the magnetite that's going to react has react. In other words, reaction half complete. So based on that, right, this is complete reaction, means mass loss of 3.4 grams right there as it mass loss tails off and achieves a constant value. So half of that's 1.7, which is right there. So the time for 1.7, taking it down there nice and prettily, a little bit more than 4. Okay, so this is 6. So 5 squares is equal to 2 minutes. So when you pop that all out, it's about 4 minutes and 12 seconds. Terribly worded question. So anyway, now we're off to another part of it. Use the graph to calculate the initial rate of the reaction, giving the unit. Well, the initial rate is what's happening at the start. And the rate, of course, as an instantaneous rate is the rate at a particular point. So you have to draw the tangent to the graph right there. So there's my pretty little pink tangent going up. Rate is change in amount over change in time. In this case, the change in the amount is mass. We're used to much more of it being concentration, but in this case it is mass. So therefore, the slope is going to be the loss of mass. Well, it goes from 0 up to this little point I've circled here. It's about 1.9 on the y-axis, 4 on the x-axis, 1.9 grams being lost, 4 minutes time gone. So that's 0.475. The units of rate are usually moles per litre per time. But in this case, we're not looking at concentration, the moles per litre, we're looking at the mass. So it just becomes grams per minute. Third part, use collision theory to explain how the rate of reaction changes during the reaction. You should consider both reactants. Well, reaction requires collisions. Now, what we got here, the important bit here, are the carbonate ions and H+ ions. Now, most reactions start with bonds breaking. Okay, so therefore what I would say is that it's probably the carbonate ions that are going to bang into something, the walls, the container, each other, whatever, and you start breaking bonds, and then you got the H+ around to take full advantage of that. So as time passes, you've got fewer carbonate ions, which means there will be fewer collisions, and if there's fewer collisions, the reaction's going to happen more slowly. Now, you could say the same for the H+ ions, okay, and the HCl, but we're told we got an excess of dilute HCl. It's fairly concentrated. It calls it dilute, but 2 moles per litre is only 1/6 of concentrated hydrochloric, so it's been diluted HCl. Like I say, not sure I'd call that fully dilute. But anyway, so you've got a limited amount of magnesite, you're putting in a big excess of the dilute HCl, so therefore, because it's in excess, I wouldn't think that that is going to have a significant issue as the rate goes on. As the reaction goes on, we're using up carbonate, we're using up H+, we got a whole lot of H+ there, only a limiting amount of carbonate. Still on this question, now we're doing it in a lump form. Okay, so we started off with crushed or powdered magnesite, so a nice high surface area, but now we've got lumps, so same amount but less surface area, thus less of the magnesite at any one time available for reaction. So anytime you use lumps instead of powder, it's going to go more slowly, and so we'll have it looking something like that. Hand-drawn little graph there showing you the reaction is going to take place, but it's going to take much longer. Another graph. Student investigating rate of reaction for the catalyzed decomposition of hydrogen peroxide to form oxygen. There's the nice little reaction. Student decided to follow the reaction by measuring the volume of oxygen, i.e. here, produced at fixed time intervals. Added spatial measure, manganese 4 oxide, 100 cubic centimeters of aqueous hydrogen peroxide, and started the timer. And here's what we get. So obviously no oxygen at the start, but then it gets produced again sharply, then tailing off until we get to a nice constant amount right here. So the first question, use the graph to calculate the initial rate of reaction. Well, as we've already done, the initial rate is what's happening at the start. Rate is always amount over time. Here the amount is the volume of oxygen over the time. So we're going to draw a tangent to the graph at 0. And there it is. Okay, again, let's find a nice point that we can read off the graph. The line goes pretty much through that intersection there of 1500 and 100. So the rate is going to be 1500 cubic centimeters of oxygen over 100 seconds, or 15.0, and again the units are going to be cubic centimeters per second. Amount, in this case volume, over change in time. Same pretty graph, but now we're going to calculate the rate of the reaction at 200 seconds. So we go up, there's 200 seconds right there. So again, we need to draw the tangent to the graph at that point. And there it is, just touching it at just the right point at 200. Now we've got to get at the slope of this again. Well, let's find a couple of points that are nice and easy to read. This point here, 100, and then 1250 in terms of the volume. And then going up here, another point there. Not quite as nice, not fully with one of these nice thick lines, but again, you've got 3 squares across there, so that's 330, and then you have 3 squares going up. Each one of those is 50, so 2150. So the slope of the line is 2150 minus 1250 over 330 minus 100, which is 3.91, and again the units, cubic centimeters per second. So the first one was much bigger than 3.91, which of course features in here. Why are the rates different in part 1 and 2? Why is the rate faster at the start than after 200 seconds? And of course it's the same argument. Reactions require collisions, so what you'll have here is you'll have one molecule of H2O2 smacking into something, getting lots of energy. Another molecule will be nearby to take advantage of that, As time goes on, we'll have fewer molecules of H2O, so fewer collisions. And then also, even if you get a good collision, fewer other H2Os being around to take advantage of it. So a slower rate. Now back to the pretty little graph. Student plotted below. Used the graph to determine the concentration of the hydrogen peroxide solution used by the student. Give your answer correct with 3 significant figures. So the assumption is that by the time we're finished here, this nice little line here is when all the hydrogen peroxide has been used up. Okay. So at that line, when it's all used up, we've made 2,000 cubic centimeters of oxygen. And that's gas. We know its temperature, we know its pressure. Well, for any gas, PV equals nRT. If you know the P, you know the V, you know the T, you can get the N. So popping them in, and I use my favorite value of R, 0.0821 cubic decimeters, atmospheres per mole per Kelvin. Seeing as how the question actually said 1 atmosphere pressure, I don't know if it assumed that you would use this value of R, or whether it wanted you to go through all the convolutions to convert that to bar or pascals or whatever. But by knowing this nice useful value of R, I can bypass all that stuff, throw in the values. So 1 atmosphere pressure, we've got 2,000 cubic centimeters, which is 2 cubic decimeters. Moles we don't know, that's the lovely value of R, and we're at 298 Kelvin there. Punch all that out, and we have made 0.08176 moles of O2. Okay, so we have enough hydrogen peroxide to make 0.08176 moles of O2. Now, of course, you need 2 hydrogen peroxides to make 1 O2, which means that we must have twice as much, or 0.163 moles of H2O2. Multiply the O2 by 2, and that's 0.163 moles of H2O2 in 100 cubic centimeters. So that's the concentration of the H2O2, 0.163 moles over 0.1 cubic decimeters, and 1.63 moles per cubic. Sorry about the abrupt end to that last one. I clicked enter before I really meant to, but you'll know I meant moles per cubic decimeter. Anyway, another part of this, a second student, right, that's different from this student, said that she had seen cobalt-2 chloride speed up the rate of production of oxygen very significantly in a different reaction. Determine how students could determine if cobalt-2 chloride is a better catalyst than manganese 4 oxide in the decomposition of hydrogen peroxide. So in other words, we're going to compare 2 catalysts, so everything else needs to be the same. So in other words, we're going to use a spatula measure. Now, by the way, a spatula measure, if you're doing a comparative amount, is actually terrible, right? Because you're not being precise enough. Okay, the spatula measure might actually be different weights depending upon different densities, all kinds of things. So you should actually get a little bit better than that. But seeing as how the first student was so sloppy as to just use a spatula, then this young lady here, second student, should also use a spatula of it. You use, instead of manganese 4 oxide here, the cobalt-2 chloride that we're investigating, use the same amount of the aqueous hydrogen peroxide solution. So everything the same, sloppy as it might be, except swapping out what you're using from the catalyst. Now, you would do those reactions, you'll compare the rates. The one with the faster rate is the better catalyst. Now, that's the A-level answer, but let's think about a couple of other things. First of all, think about the cost. Right? Maybe manganese 4 oxide is extremely cheap. Cobalt chloride is extremely expensive. You have to think about what kind of improvement in speed makes it a worthwhile substitution. Something of great other issue is health and safety. Manganese 4 oxide is nothing. It's completely innocuous. It just looks like sort of powdered charcoal. It's fine. Cobalt chloride, on the other hand, is a danger for the aquatic environment and so on. So even if cobalt chloride's much better performer than manganese oxide, it's more expensive and it's more hazardous. So always think about such things, even if the A-level exam is not looking for those.